So this video is to provide a brief explanation of double integration from the perspective of single integration. Okay, so let's start with the basic setup for the single integration. The single integration is to basically calculate integration. For example, here a function of fx over x for the interval from a to b. So that's the basic single integration. What it means is try to figure out the area of the shaded area, assuming that my function fx is for the range of xy is given by this this curve. So this is the area, the size of the shaded area. So computational wise, it can explain by this. So we'll first compute what is the fx times dx. So fx is, for any x we can calculate fx. For example, given x over here, so fx is the value we get it over here. This is fx, and dx is a small change of it. Okay, it's a very small, tiny change. Okay, so fx times dx is the area. Is this small, tiny area, the slice. Okay, so what the integration means is to compute the summation of all the little tiny slice, and you compute all the slices, and you do the sum of this. Is you try to calculate the sum from the beginning to end, which is essentially try to calculate the size of the shaded area. Okay, now let's move to the double integration. The double integration talks about an integration over an area rather than just an interval from a to b. Let's say we talk about area created by typically the areas can be represented by some region. Is a region that has a bound for the variables. For example, here we can define, let's say, a given area which is given by the triangle over here. So we can represent the area as x is less equal to 0 but greater than equal to 0 but less than y, and y is starting from 0 to 2. So that will represent this triangle area. So double integration is to integrate a function f gxy. Okay, gxy we can interpret it as for any point in this area I can define some scalar value gxy. Okay, one way we can interpret this is assuming that this is for a small even area, any point. We can have the gxy represents the volume of liquid, let's say water, we have for this point. So this integration is try to calculate the entire volume of water associated with this area. So notation wise, this can be written as gxy. Okay, gxy is, again, this is for any point we can define gxy, and d sigma is an infinitesimal cell which is around this point xy. So you give it a point of here. This is a very tiny small cell around this area. So you do this product. This will be just the volume water or liquid we collected for this very tiny small cell. If you integrate over an entire area S, we get the volume, right? So that's the standard double integration. Because we don't know how to calculate the integration for this d sigma, we only know how to calculate it from one dimension, one variable, because this is d sigma. We don't know if what's the relation between d sigma and dx and dy. So the first one is the immediately thought is, if we could write a d sigma is sort of x and y, we hopefully can decouple this one into two integrations, right? So we know how to integrate for one variable. We don't know how to integrate two variables at the same time. But if we could integrate a variable, we can calculate this one by integrate two different compute two different single integrations. Then we can compute the outcome. So the basic idea is we try to rewrite d sigma as dx and dy because this is a small tiny cell. If we make it larger, this is a small tiny cell. So it's nothing but we put this little dx, this dy, and this little dx. So this is a little c. They also represent a small c around any xy. So that's okay. Now this can be equivalently written to replace d sigma, and we still have gxy. Now the problem comes to the fact, how do I determine the lower bound and upper bound, because that's required for the single integration. To interpret that, we just want to take a look at what's the meaning of inside. Okay, this is the inside one is called internal integration. The outside one, we call it the outside integration, okay, or outer integration. So the way we can reason this way form is to consider, when we do the internal integration, we consider y to be a constant, because when we do the integration for inside, it doesn't integrate over y. So we only integrate over x. We assume this x to be a constant. So what does it mean? Let's go back to this one. If we assume y to be a constant, let's say this is my y, some y, let's say y is 1. So what is this inner integration trying to do is try to calculate the sort of volume of water for the water for this small tiny area. When we let, for this one, we type this is a slice, we cut it into slices. This is, for this slice always has same y. We calculate this one, and this one has dy as its width. It's a very, very tiny one. This inner try to calculate this volume. I should say this. The inner is try to calculate volume for a small slice. So this is a slice, what I mean by that. Okay, so by looking at that, we can see for different y's the slice can change. Because if you start from when y is 0, let's say y is 0, the slice is this. When y is 1, get shorter. When y is 2, it's just nothing over here. So the way we define the size of slice depending on what the actual value of y is. So by looking at this relationship, this line represents when y is equal to x, which means if y is 1, I know this x is also 1 according to relation. So this so the starting point here is already depending on y. So if y is 1 is 1, y is 2 is 2, y is 0 is 0. So this is just because this one has to apply for all different x of different y. So this one has to be y, because for different y I have to have different starting point. Well, my ending point is always 2, doesn't matter. It doesn't matter which y is. So this is 2. Now for the outside, what it means, you can now interpret the inside one as what? The internal integration as a scalar function. It's like fx. You can evaluate fx. Of course, this will be fy because the outside one is a function y. You can evaluate as a function y. So this scalar function is the volume for each slice at different y. You sort of, if you consider this as compared to this one, you sort of try to consider, hey, if this is my fy is just the volume water, I calculate at a different point, at a different y. So what do? You just do one more integration again, right? So according to the interval, the lower bound, upper bound is just like the standard one. It's just from whatever y you can select. So y I can select from 0, because below 0 I don't have anything. And about 2 there's nothing, so you just start from 0 to 2. So that'll be done. Okay, so I hope this is helpful for you to understand what the double integration is trying to do, and what's the relation between the double integration and the single integration, and how we figure out the lower bound, upper bound. Okay,